So all we have been discussing is the wave behavior of light. At the beginning, I made an introduction about the fact that light was a complicated thing to study because sometimes it shows a wave behavior, sometimes it shows a particle behavior, and people kept changing their mind as new evidence came about one thing or the other. They kept changing their mind. The consensus at the end, after quantum mechanics was developed, is that it's actually something that is both of them. If that ever makes sense, that something can be a particle and a wave, well, that's what we're stuck with. Light is something that is both particle and wave. But so in certain circumstances, certain experiments that you do, certain setups that you have, you will see the effects of light being a wave. But in other setups, you will not be able to see those effects, right? So we just discussed what you would do when the wave nature of light it's evident, it affects the results. So we saw that light spreads out, that it has rings, interference, all that stuff, right? But there's going to be a limit or a transition between those effects and the more familiar effects that you and I are familiar with, which are that light propagates in straight lines, right? You see the shadows of objects is defined by the line that connects the edge of the shadow with the edge of the object and the source that is producing the light, and this seems to be a straight line. So how do we go from one to the other? The connection is through the equation that we saw before. So let me just, if you have a small aperture and you send light through this thing, and you put a screen here, then we know that the light is going to spread out. And the central maximum is going to have a width given by 2.44 times lambda over d times L, right? Let's just leave the L fixed and see what happens as we start making. We know what happens, we just talked about that, when the D is smaller, right? D just opens up and opens up and opens up. But what happens when you make the D big? When you start making the pinhole bigger and bigger and bigger and bigger. You know that the limit case, which is when the pinhole is big, you know exactly what you are going to see on the screen, right? You have many years of experience looking at the images of objects. You would see a circle that is, if the source is far away, will be the same size as the size of the aperture, right? That's what you would expect. But there is going to be a limit case. So this will be the case. So this is the wave. This will be wave optics. So light is behaving as a wave, and it shows up very clearly. And that happens when D is small, right? It's small or about the same as the wavelength. What happens when you start making D bigger? So what's going to end up happening is that if you put your screen, say at a typical distance in a lab of 1 meter, or in a room, a human room, which will be meters in size, not kilometers, not millimeters. If you say that this L is the distance to the screen, there will be a diameter of the aperture that on your screen will produce a diffraction pattern that has the same width as the diameter of the hole. So you're moving towards the case where the image that you see on the screen will match perfectly the shape and the width of the hole that you allow the light go through. The limit case is that when W, the width of the central maximum, matches D. This is the transition, right? Or the transition between wave and particle picture of light. So let's spell out what that means in terms of an equation. If the width is going to be equal to, of the central maximum, is to match the diameter of the hole, then that means that 2.44 times lambda over D times L should be equal to D, the width equals to the diameter of the hole. So that implies that d squared is equal to 2.44 lambda L, and d is the square root of that. So if you replace typical values, like I said, for human experience with rooms of distances between screen and setups of a meter or a couple meters, let's say that L is about 1 meter. And if we're looking at light, which means that the wavelength is going to be of the order of 500 nanometers, between 400 and 650 or something like that, 700, let's take some value, which is 500 nanometers. You plug in those two numbers, you will get a diameter for the pinhole of about 1 millimeter. So if you do an experiment where you're blocking light by, you have a screen and you make a little hole in it and you're looking at how this light is going to propagate, if the diameter of the hole is smaller than 1 millimeter, then the central maximum is going to be bigger than the diameter of the hole, which means you need to consider that light is spreading out like that because it is a wave. So the limit case is when d is about this much. The limit that we're talking about is when this distance is about that much. If now you make the aperture bigger than that, what ends up happening is that the aperture diameter is very big, the screen is over here. D very big in your equation implies that theta 1 is very small. Lambda divided by d is theta 1, right? So your theta 1 is very small. So the first fringe happens really close to the middle of the aperture, really close. So close that they cannot be distinguished, but also the intensity of those bands is very great. So this is what you will have. And suddenly a lot of intensity like this. And as soon as you move away from this position, this point and that point, which matches the width of the aperture, then the intensity decays very quickly. And inside here, the width of the fringes is so tiny because it depends on lambda divided by d is so tiny that you cannot see that. You cannot resolve that. So it just looks like a white bright spot on the screen that matches the shape of the screen, of the hole on the screen. And this is where you are in the ray optics regime. Because now you can forget about all this interference between different parts of the wave and forget about the wave spreading out like that. The simple picture that you can have in your mind is that your wavefronts are moving towards the screen and they're moving in that direction, right? That's the velocity of the wave, perpendicular to the wavefronts. And this, you can think of these light rays, which are, because light is also a particle, you can think of the photons having these trajectories, right, moving in a straight line. So some of the photons get blocked here and here, some of the photons go through, and when they hit the screen, they produce an image on the screen that matches the shape of the aperture. So instead of drawing your wavefronts that are going to be like this and they're not opening up anymore, in the ray optics regime, we forget about the wavefronts. They don't do anything useful for us anymore, and we just draw these lines, which are, like I said, they represent the trajectory of the photons that make up light. So you imagine in ray optics, you imagine these streams of photons moving in space in straight paths. And sometimes they get blocked, sometimes they don't get blocked. Sometimes they, as we're going to see in refraction, their direction of propagation gets changed. You can do that.